Hi, I am Maddalena Zuccotto, PhD student, and the work I present concerns learning environment properties in partially observable Monte Carlo planning. This talk is structured as follows: context and problem definition, background, methodology, experimental evaluation, and finally conclusions and future work. Let's start with the context. Planning is an important problem in sequential decision making, and it widely pervades artificial intelligence and robotics. In recent years, artificial intelligence techniques were applied to several contexts, such as smart buildings, industrial machinery controllers, and mobile robot navigation, and we have observed several applications of reinforcement learning techniques to solve sequential decision-making problems in partially unknown environments with promising results. Some properties of the environment cannot be represented in the model of the dynamics, but they are important to solve planning tasks, and in particular to probabilistically reduce the state space. In this work, we tackle the specific problem of learning probabilistic state variable relationships to improve planning performance. For example, consider the rock sample environment in which 5 rocks, depicted as gray pentagons, are placed in fixed positions on a 5x5 grid. Each rock can be valuable or valueless. The agent, the circle, knows the rock locations, but it cannot observe rock values, that is the hidden part of the state. At each step, the agent performs one action among moving, checking rock value, or collecting rock value, and the goal consists in maximizing the reward. Learning state variable relationships here means learning the relationships among the value of different rocks. The rationale is that if the agent knows that two rocks have the same value with high probability 0.9 in the image, it can improve its planning performance because once it has observed the value of one rock, it has also acquired some knowledge about the value of the other rock, and it can plan considering that knowledge. In the first row of the image, we have the action performed by the agent without any knowledge about rock values relationships, while in the second row, we have the action performed exploiting such knowledge. In this case, the agent performs a sensing action to check the value of rock 1. As we can see, at step 5 in the second row, once the robot has observed rock 1 as valuable, it has also acquired information about rock 2 and 3. To better understand the advantage given by the knowledge, suppose that the agent has to repeat the sensing action 3 times to be sure about the value of the checked rock. At step 10, exploiting acquired knowledge about rock values relationships, the agent has already sampled rocks from 1 to 3. While, without any knowledge, it has only sampled 2 rocks, and in this case, the agent needs 16 steps to collect them all. The decreased number of steps necessary to collect the 3 rocks corresponds to an improvement of 37.5% against standard POMCP. Our goal is to learn probabilistic equality relationships among state variables during standard POMCP execution on the left in the image. This means learning the potentials of a pairwise MRF, which will be used to boost the belief during the application phase to obtain a performance improvement. To this aim, we propose 3 methods to learn state variable relationships while the agent acts in the environment. And we present a criterion for stopping the learning process based on confidence intervals of MRF potentials. Finally, we empirically evaluate our approach onto robotics-inspired domains. As previously said, in complex domains, the environment is only partially observable. To model uncertainty in this context, partially observable Markov decision processes were introduced. In the POMDP framework, the agent is not able to directly observe the current state, namely, the presence of the tiger or of the treasure chest behind the door. This is the hidden part of the state, and it can only be inferred using observations returned by the environment. Thus, the agent maintains a probability distribution over states, called belief, updated at each time step. The agent's goal is to maximize the expected discounted return acting optimally. A solution for a POMDP is a policy that maps beliefs into actions. The computation of optimal policies is in general unfeasible, therefore approximated solutions are typically favored. POMCP is a Monte Carlo-based algorithm for planning in partially observable environments with large state spaces, to compute an approximated policy with a particle filter representing the belief. To store the probabilistic relationships among state variables, we use Markov Random Fields, that are undirected graphs in which nodes represent variables and edges represent probabilistic relationships between variable values. As an example, consider the MRF represented in the image. On the edge between state variable 2 and 3, the value 0.9 means that the probability to have the same value in 2 and in 3, namely both variables have value 0 or 1, is 0.9. In this work, we propose 3 MRF learning methods, one based on the information gathered by the agent when it gets the true value of state variables, and 2 on the information present in the belief. The first method we propose is the sample-based MRF learning, shortened to SL. We assume that the agent can somehow get the true value of state variables, for example, collected the rocks through the sampling action in rock sample. We use this information to update the count of equalities and inequalities among pairs of state variables. Then, we compute MRF potentials by normalizing the count, and finally, we consider equality probabilities. The second learning algorithm we propose is the maximum likelihood belief-based MRF learning, shortened to MBL. It leverages information from the state with the highest probability in the belief. At the end of each episode, we extract the state having maximum likelihood in the belief. We use the state variable values in it to update the count of equalities and inequalities among pairs of state variables. Then, we compute MRF potentials by normalizing the count, and finally, we consider equality probabilities. The third learning algorithm we propose is the weighted likelihood belief-based MRF learning, shortened to WBL. It leverages information from all states in the belief, weighted by their likelihood. We use these values to update equality and inequality probabilities. Then, we compute MRF potentials by normalizing the counts, and finally, we consider equality probabilities. To decide when the learning process can be stopped, we propose a criterion based on confidence intervals of state variable equality probabilities in the MRF. At the end of each learning episode, for every edge, we analyze the sample size, and we compute the confidence interval. We stop the learning phase when all the sample sizes are large enough and all the confidence intervals do not include the value 0.5. As we can see in the image from episode 22, all confidence intervals lower bounds do not include value 0.5, represented by the black horizontal line, but sample sizes are too small to stop the learning process. Both the conditions are satisfied at the end of episode 28. Thus, we end the learning phase, and the learned MRF can be used by POMCP to obtain a performance improvement. In our experimental evaluation, we performed 2 different tests. Test 1 is aimed at comparing the performance achieved by the 3 MRF learning methods after a fixed number of episodes to identify the best learning strategy, whose performance are analyzed depending on the number of learning episodes in Test 2. Our tests are performed in the rock sample domain, with 8 rocks on a 5x5 grid. The rock value configuration changes at each episode, respecting the true state variable relationships depicted in the left bottom corner, in which the MRF presents a click between rocks from 1 to 6, represented by the nodes of the graph, and edge probabilities are set to 1. Value of rocks 7 and 8 are instead randomly assigned, since there is no constraint on their values in the MRF. This MRF is the one we aim at learning in our tests. For each test, we perform 5 runs of 100 episodes at most, and every episode is composed of 100 steps. POMCP always performs 100,000 simulations and initializes the particle filter with the same number of particles. We evaluate the proposed algorithms using 2 performance measures: the discount return, defined as the difference between the return achieved with and without the MRF, and the MRF distance, which is the average Euclidean distance between the equality probabilities in the true and in the learned MRF, normalized by the number of the edges. In test 1, we first learn the MRF with the 3 methods. Then we insert the learned MRF in POMCP and compute its performance. The picture shows that the best performance in terms of discount return is obtained with MBL, with a median of 3.92, followed by WBL, with a median of 2.19. These 2 values are the correct ones. There is a typo in the paper. As we can see, both methods achieve a performance improvement since they use the information in the belief that comes from observations. Obviously, the median obtained using the true MRF is the highest one, with a value of 4.10. With SL, instead, we obtain the worst performance because it uses only information from collected rocks, and POMCP tends to collect only valuable rocks. hence the information is partial and the MRF is not accurate, leading to a performance decrease. These results reflect the final distances between the true MRF and the learned ones. As we can see in the table, the lower value is achieved by MBL and the highest one by SL. Test 2 only considers MBL. We learn the MRF for different number of episodes, as we can see on the x-axis of the image on your right. And then we use the learned MRF in the remaining episodes until the 100. Analyze the average difference of final discounted return achieved by MBL compared to standard POMCP. We see that the performance obtained with the MRFs learned with more than 5 episodes are higher than that of standard POMCP, with a maximum obtained with 40 episodes. Using 1 and 3 episodes to learn the MRF, we have a performance decrease due to over-specialized MRF on the relationships of few episodes, and they do not generalize enough the true probability distribution among state variable values. On the other hand, ending the learning process too late, we limit the possibility of exploiting the learned MRF to obtain a significant performance improvement, despite its higher accuracy, because we use it only in few episodes. In the next test, we combine the MBL with the stopping criterion previously described, and we analyze its performance on 2 MRF topologies. The two pictures depict the quality relationships we aim at learning. We consider again the rock sample domain with 8 rocks on a 5x5 grid. Here, the MRFs are represented on the grid. The ID of each rock represents a node, and the probabilities on the edges are set to 0.9. For each test, we perform 10 runs of 100 episodes at most, and every episode is composed of 70 steps. POMCP always performs 100,000 simulations and initializes the particle filter with the same number of particles. We evaluate this approach considering also the belief state distance, which is the weighted average Manhattan distance between the agent belief about the true state and the true state itself, achieved with standard POMCP and using the MRF. Here, the main result is the difference in discounted return achieved using the learned MRF compared to standard POMCP, that is 172, and it corresponds to an improvement of 8.35% in figure B. This improvement comes from a very high similarity between the true MRF in figure C and the learned MRF in figure D. This is also confirmed by the value of the MRF distance in the table, which is 0.04. Moreover, in the table we show that using the MRF we get a significant decrease in terms of average belief state distance, obtaining a value of -0.16. We repeat the test on the second MRF topology in figure E, obtaining similar results. In this case, the difference in discounted return, figure F, is 1.36. That corresponds to an improvement of 7.16%. In figure G and H, we see the high similarity between the true and the learned MRF respectively. The quality of the learned MRF is again confirmed by the value of the MRF distance in the table, which is 0.03. And we obtain again a significant decrease in terms of average belief state distance with a value of -0.14. To conclude, in this talk we present an approach that combines MRF learning method with a confidence interval-based criterion to stop the learning process and to start using the MRF without performance loss. Results show that this approach is able to produce MRFs informative enough to achieve a performance improvement. Future research directions aim to adapt the learned MRF to specific episode characteristics during the application phase, and we are investigating the possibility to integrate the learning process with planning to optimally balance the exploration and exploitation trade-off. Finally, we are implementing the proposed approach on real robots, namely on turtlebots. Thank you for your attention.